Okay, you can turn to page 2 in your packet. We're going to finish up 6 on page 2. We did 9. Okay, we did 9. Okay, so let's try number 6. This is still first derivative test, but it's asking to find relative max and relative min. So find f prime, set f prime equal to 0, create your f prime sign line. Okay, try that. You guys, several empty slots on the wall there. If you guys can put your phones up, your phones aren't up there. Okay, so we find f prime. Right, we set f prime equal to 0. We factor out the 3, continue factoring, trinomial factoring. We get solve for x. We get 9 and -1. We replace -1 and 9 onto our derivative sign line. We choose values in each subinterval. I can choose -2. I can choose 0. I can choose 10. I'm going to insert all the test values into my first derivative factored form. That's the easiest one for me to quickly gather the sign of my interval without having to go through a bunch of messier calculations. And then if I plug -2 in, I'll get negative times negative, which is positive. If I test 0,
I'll get negative times positive, which is negative. If I test 10, I get positive times positive, which is positive. So based off of these arrows are helpful. It kind of helps us see how the graph is rising and falling. And this is only asking for relative extrema. So we plug negative, we see that there is a relative minimum, sorry, relative maximum at x equals -1. Sorry, my key shows x equals 1. It should say -1. And make sure that you are writing out your because statements. I think we tend to be good with because statements for increase, decrease, but we tend not to be as good with relative max, relative min. So make sure that we understand there is a because statement, there is justification for relative max, relative min. And we say because f prime changes sign from positive to negative for relative max and for relative min is because f prime changes from negative to positive. Make sure that you're naming whatever that's changing sign, that you're not saying the graph or derivative, right? You want to be specific.
So you can say it like just like instead of positive, right? In words positive and negative, you just put the plus and minus.
Either one, yeah. You can write it out positive to negative, or you can write plus to minus. Yeah, College Board will accept either form. Okay, any questions with first derivative test? I think most of us find this pretty straightforward. We've seen this already from particle motion. Number 7, this is find intervals where the graph is concave up, concave down. So this is called the test for concavity. We do the same process. It's just that it's with a second derivative function, right? So make your way down to f double prime, set f double prime equal to 0, find your critical points. Test your intervals. But now positive is going to represent concave up and negative is going to represent concave down. Okay, try those steps. Okay, so we have f prime, power rule, f double prime, power rule again, set f double prime equal to 0. There's only one critical point. Now, just because we see a critical point, it doesn't mean that we can call it point of inflection. We got to put this onto a sign line and verify that there is a change in what?
Direction.
Signs. So if there's no change in signs, then this critical point will just remain a critical point. It's not a point of inflection until there's a change in sign. The order of sign change does not matter as long as there's a sign change. So if there was a critical point with no sign change, then there will be no point of inflection. Concave up because f double prime is greater than 0. Concave down because f double prime is less than 0. Point of inflection at -1/3. If I ask you for the y value, you would insert the -1/3 where? Back to the
Next step.
of
The
original, right? Original is going to give you information about location. F prime gives you information about slope. F double prime gives you information about curvature or concavity. And your reasoning is because F double prime changes signs. So pay attention to your justification for concave up, concave down, and for point of inflection. I inserted the -1/3 back to the original equation. Plug that in the calculator, whatever that y value gets you, whatever the y value you get in return, that's your y value
for that order pair.
You said fx is for location, f prime x is for like
Slope,
slope, and what is f one?
concavity,
You got it good.
curvature. All right, everybody good with 7? All right, here's number 8. Number 8, we want to use the second derivative function. I want to make sure I go through this in detail. This is something that where the steps don't feel as yeah, we got to get used to these steps. These are not as intuitive as first derivative test and test for concavity. So second derivative test does the same thing as the first derivative test. Okay, it finds relative max and relative min. It doesn't find point of inflection concavity, right? That is test for concavity. So if you want to find relative max, relative min, that means you're going to find critical points from where? From first derivative, yeah, from f prime. So we're going to start off the same way as first derivative test. We're going to find f prime and set f prime equal to 0. Okay. Factor out of 2. Yes.
On the key says that it's negative 20x.
Oh, sorry. Yeah. Otherwise, it's not going to work. Thank you. Sorry about that. I made the change on the key, but not on. It multiplies to be negative 30, adds it to be negative 1. Yeah, sorry, negative 20x. Okay, so it's going to translate all the way down here. Let's see, 3x squared plus 5x minus 6x, that's negative 1x minus 10. So this works. We find our critical points from here. These are our candidates for relative max and relative min. Okay, we'll set these off to the side because we're going to use these. These are our candidates. We're not going to do the f prime sign line, even though you could use f prime sign line to double check your work. But the work I'm looking for is second derivative test. So we have to now move on to the second derivative function. So f double prime. Go through power rule again. 12x minus 2. Okay, do we set this equal to 0? No, that's test for concavity, right? That's something else. We're going to involve these critical points and plug it in for the x of that double prime. Okay. So 12 times negative 5/3, that's the same thing as -4, sorry, 4 times -5, -20 minus 2, which is -22. Now, we have to understand something. This is not order pair. It's hard to visualize what this really means. We just know it's some sort of a curvature value. But the important thing for us is don't pay attention to the number, pay attention to the what? The sign. The sign is what? Negative, less than 0. That's really the only thing that we care about from this number. Trying to think about what that number looks like. It's that's where we can kind of, it feels confusing, right? It's not order pair, it's not slope, it's how curve, how much curve this graph is experiencing. And all we need to know is that this is part of a concave what? Concave down. That's all we need to know. And if the graph is concave down, the graph looks like this, the graph looks like this, then a slope 0 on a concave down graph must be a what? Relative what?
Max.
Max. So we say relative max at x equals -5/3. Why can we not say -5/3, comma, -22?
Not a Y.
That's not a y value, right? So do not include -22 in any of your answers, right? This -22 is throwing a lot of students off because you feel, well, first, we think that's a low number, so we want to say relative minimum. And second, it's not an order pair, so we don't want to include that in order pair either. So basically, you just want to know that it's negative, and then that's it. Relative max is this point. If I want to find the y value, I would have to go back to my original equation. So do understand that students have trouble with this because our natural tendency is a negative number is a low number. We want to say relative minimum, but you have to understand that this is not a location. This is a concavity. Concave down looks like this. This is not a relative min, that's relative max.
That's not part of it, right? You still have to do the,
I'm sorry?
you still have to do plug in 2, right?
That's right. We still have plug in 2. Good.
Do we have to do like, because for things?
You don't say because you just have to show that this number is less than 0. You can make it, you can just go from here to here. But I find that students have easier time making, avoiding a mistake if they can write concave down and draw the shape. If they can do this, then it's harder to make a mistake. Does that make sense? Okay, f double prime of 2. Into the second derivative, so 2 times 12. Sorry, 22. That number is not important. It's really what? What's important about this number? That is what? Positive. So positive value means,
It's gonna be a concave up.
and concave up looks like this, which means that this is what?
Relative minimum.
Relative min. Now, there's a special case that I haven't gone over yet. I want to talk about that special case. Now, let's say there was a critical point at x equals 1/6. Okay. Let's just say for just for demonstration purposes. And let's say I want to test 1/6. So I test 1/6 in for x. What do I get? 0. Now, this is neither concave up nor concave down. So we're not able to visualize what's happening here. So if your second derivative is giving you a 0, any idea what can we say?
Only concave. The opposite one.
It's not conclusive.
Oh,
we don't know what's going on. We would have to, it's either neither. It could be relative max, it could be relative min, but we have to go back to the first derivative test because this is not going to help us. So first, it's hard to use, right? And it's not fully going to give you a great picture. So, you know, if we were if we had to choose, we would just always choose first derivative test because it's always going to give us something that's conclusive. And this feels like a roundabout way of doing things, but we still need to be responsible for this. So understand that if I ask you for the second derivative test, positive would mean concave up, relative min, negative would mean concave down, relative max, 0 would mean inconclusive. And we don't know exactly what's going on with second derivative tests. We just don't have enough information.
So it wouldn't be like a sharp curve, right?
It would not be a sharp curve because it's already coming from a place where the slope is 0. So the graph could look something like this, where it's neither a relative max or a relative min because it's not a.
What if the upper like function you plug in works though?
I'm sorry.
What if the upper function you plug in works then? Because you know how to do different x values.
Mm-hmm.
What if like one of them is 0, but then the other one's like, still gives you a value?
Yeah. So if one of them gives you 0, then one will be inconclusive, and then the other one, if it gives you a value, then you can determine whether it's positive or negative.
Okay, so it's kind of two separate.
Yeah, depending on it could be any one of those three options, right? Either a positive value, a negative value, or a 0. Positive and negative, we can make strong conclusions about. A 0 we don't. We will have to go through a different method. Okay, let's go to worksheet 3. Page 9. So critical points, what are our steps here? We find what? F prime. And we set F prime equal to 0. Now, if there's a numerator and denominator, we'll have to look at both. And if we have fractions, we'll have to do common denominator. Okay, so what's my new denominator there? I'm sorry, what's my 8/5 x to the what? 8/5 minus 5/5 is
3/5.
3/5.
Negative 2/5.
Okay, we gotta clean this up, right? We got some fractional variables we gotta deal with, so let me clean this up. All right, so we want to look for critical points in the numerator and denominator, but it's hard to do it. Sorry, it's hard to do it when we have fractions that are not together. So guess what? We have to find what? Common denominator. Okay, question?
Just confused how you didn't get a negative 3/5. Like, why you didn't put that on the bottom? There's like 5 of them.
Oh, right. So 8/5 minus 5/5 is 3/5. 3/5 is not a negative exponent, so it can stay up here. A negative exponent, we can bring the variable back down to force a positive exponent. Okay, so what's our common denominator? Yeah, 5x to the 2/5. That's large enough for both to multiply into. So what's missing between my first denominator and my new denominator?
The 5 and the 2/5.
X to 2/5, right? This, I need to multiply 5 by x to 2/5 to get my new denominator. So I need to multiply the top by that same value. I need to balance my fraction, right? So 5 times x to the 2/5 is 5x to the 2/5. I need to do the same thing with the top. 8x to the 3/5 times x to the 2/5. What does that become?
It's 8x 1, so it's
Good.
8x.
We add exponents, right? 2/5 times plus 3/5 is 5/5, which is 1. That's nice. I'm just left with 8x.
It's like,
Well, do we see any difference between the old denominator and the new denominator here?
oh no, you didn't multiply by 5.
Right, so this one is good, right? So no adjustment needed. So the numerator can stay as 3. So now we have a nicely cleaned up derivative that is all under one fraction. And now where can we look for critical points? And denominator. So both set both equal to 0, solve for x separately. So here, subtract 3, divide by 8. This one you would divide by 5, raise both sides to the 5/2, which is really just gonna still be 0.
Oh, so you don't do like 1 over something, what's the denominator?
No, yeah, you can just set the numerator equal to 0, denominator equal to 0, nothing complicated. You don't have to do anything more complex than that.
Why don't you bring the 5 over when you make the common denominators, because it's the same values each side?
I do, right? My 5 is part of my common denominator. What's your question again?
Oh, I was gonna say like multiply that 5 to make it 25x 2/5. And then
Well,
25.
That's a little too big, right? We don't have to, right? Yes, 25x 2/5 can be a common denominator, but it's too large, right? If 5 can go into 5, if both can go into multiply into this, then 25 is too large, right? Because we can do 125, we can do 625. But why choose such large numbers when both of these can multiply into 5 already? Now, if it was like, let's say if it was like 5 and 3, then now I have to choose 15 because I need a number large enough for both 5 and 3 to multiply into. But if 5 and 5 are both the same number, then there's no need to include a larger number.
Okay.
Right. Okay, next up is extreme value theorem. So extreme value theorem, I have that on the board there. If my function is continuous, I need to establish the function is continuous. That means if you don't see any variable in the denominator, if the vertical asymptote, if there is one and it doesn't influence or disrupt your interval, then we're safe, our function is continuous. But obviously, if there is no denominator variable, then the function is continuous. Your steps then is find critical points, find f prime, set f prime equal to 0. Make sure your critical points are valid, and then test valid critical points along with the endpoints given into the function and compare the y values. Highest y value is your absolute max, lowest y value is your absolute min.
That's into the original.
Into the original, yep, into fx. Yes.
On the roles there, once you establish f of a is f of b,
Yeah.
do you set f of x equal to the m or to 0?
Equal to m, which always will be 0. Because if your y values are the same, then the slope between the endpoints is always going to force that to be 0. Okay. Now, extreme value theorem, does this require the function to be differentiable
Yes.
for extreme
No,
value?
no,
theorem?
no, it's
It doesn't, just continuous. Rolle's theorem, I need 2 conditions. Mean value theorem, I need 2 conditions. But extreme value theorem is only this condition. Right, so so a couple of mistakes that students make on the quiz. Either students don't include conditions at all, or they add too much in a condition. So they feel like, oh, every theorem is going to be 2 conditions. So they include differentiable for extreme value theorem. You'll lose a point there. So make sure extreme value theorem only has continuity condition. Rolle's theorem and mean value theorem has continuity and differentiable condition, because these are talking about slope. So we need a smooth curve. This one, slope is not important because we don't want to discredit a function that has a sharp turn because we're just looking for max and min. We're not trying to guarantee slope.
But you're just on the other class, so you can.
Mhm. Yeah, I'll leave it so you can take a picture. So, we established our function is continuous, is a polynomial. It's nice and, straightforward. No issues there. We find f prime. We set f prime equal to 0. We basically are looking for critical points. Okay, but every time we find critical points, we have to kind of step back and ask, are these valid critical points? And what can we say about these critical points?
Yes, they are.
Yes, they are, because
Because they both fall within -2 and
good, they fall between -2 and 3. So we have 4 points to test. And we're going to insert all the endpoints and critical points into the what? Back into f of x, right? Back into the original function. So, again, if you want to save time by using the alpha trace, you can, but not a huge deal if you don't. Alpha trace will get you that Y1 menu, and then just spend time to plug in each of your critical points and endpoints. Just give me the Y value or give me the X value to the side, but don't give me order pair. Order pair, that means you're showing me that they're equal weight and they're not, right? It's the Y value that is the emphasis. So if you leave out the X value, I'm fine with that. But if you want to include the X value, don't put it as an order pair. Put it to the side.
what's the Y value then?
Just the Y value, yeah.
For the -2, or do you flip that in to get negative?
Back into the original function. Yeah. Everything goes in the original function because we want to compare their physical locations. All right, everybody good with the extreme value theorem? Okay, Rolle's theorem is on the board here. So Rolle's theorem says, what's the minimum amount of information that needs to be given to me to guarantee there's a slope 0? So I need to confirm that function is continuous, differentiable, and that the endpoints are the same Y value. And then it's going to feel just like mean value theorem. You're still going to find the slope between the endpoints. You're still going to find the derivative. You're still going to set them equal to each other. But it will feel like finding critical points because if your endpoints are the same, then your slope is always 0, and you're going to set f prime equal to 0. The only reason why we don't say, oh, this is just finding critical point is because with Rolle's theorem, it needs to have a slope 0 on that certain interval. With critical point, we don't care what the slope 0 is. We're just looking for slope 0. But Rolle's theorem, it has to be a slope 0 on that interval. So let's look at number 3 here. Here's our function. This is not a polynomial, so we got to pay more attention here. What could cause an issue with this function? X plus 2, right? There's a hole or asymptote at where? At -2. But just because there's a vertical asymptote, does it mean that we can automatically say that function is not continuous? No. Because we only care about continuity where?
-1.
Yeah,
So-
-1 to 3. And this one is inside or outside the interval?
So
Outside. So this one is, so we saw that there was a vertical asymptote, but it's not disrupting our interval
our interval is going to be safe. So we can continue forward with Rolle's theorem. Yeah, or gossip and holes. So if you can make the first condition pass, the second one will follow along with it.
As long as the bird weapon doesn't like impede, then it'll be continuous.
Exactly.
And differentiable too.
And differentiable too. Yeah. I won't give you one where it's continuous but not differentiable. They're both gonna if you can make the first one pass, the second one will go along with it.
You bracket the continuous one, but
That's right. Bracket the continuity, parentheses with differentiable. So I'm really picky about that on the quiz as well. I want to see the proper notation for your conditions.
some quiz that look just like this.
Yeah, more or less. I mean, it's going to be 9 questions, 1 of each type. Yeah,
Your whole class too.
yeah, whole class of it. Okay, what's next? We're going to find no derivative yet, right? We want to spend the time to find order pairs, right? So just like mean value theorem, we're going to plug in our order pairs first. Nine minus 6 is 3. 3 minus 3 is 0. 0 over 5 is 0. My average rate of change, you can already tell, but I can still go through this. If you feel like you just want to just go through the same steps between mean value theorem and Rolle's, that's fine, because that just feels, then it feels more similar, right? Because you're really just finding your slope between the endpoints, just like how you do with Rolle's theorem. It's just that your average rate of change is always going to end up, or should always end up being 0, because these are the same y values. So is Rolle's theorem going to pass? Can we guarantee a slope 0? Yeah, because not because these are both zeros, because these are both the same y value. If you have the same y value, then they're always going to cancel out to be 0. Okay, so we'll set f prime, find f prime next, right? Find the average rate of change, then your instantaneous rate of change. But this, we got to go through what? To find the derivative. Quotient rule, right? Quotient rule. Okay. F prime g minus f g prime all over g squared. There's my instantaneous rate of change, or formula for my instantaneous rate of change. This is my average rate of change. What am I going to do with these? Set them equal. Now, if I set them equal to each other, what does that really mean? especially when I have a numerator denominator fraction here. How would you proceed from here? Correct. Yeah, so basically, yes, you can cross multiply. You can always put a 0 over 1, cross multiply, and the denominator goes away. But the big idea here is that we're looking for slope 0, so the denominator is not going to tell us anything about slope 0. It'll tell us vertical asymptote, it'll tell us holes, it'll tell us sharp turns, but it's not going to give us anything about slope 0. So another way to think about it is it's just the numerator that we care about. Because if I'm looking for slope zeros, it's not going to come from the denominator of the derivative. It's only going to come from the numerator of the derivative. Now this one is not factorable. Okay, you have to go through quadratic formula. I won't give you a quadratic formula on the quiz, but here we go through that process. But I do want to point something out here. Quadratic formula will give you two solutions, but do we keep both solutions? And how do we know which one to keep? Right. What do we know about location of mean value theorem problems or Rolle's theorem problems? Has to be between, that's right. So you would plug this into the calculator, plug this into the calculator. If both of them are inside the interval, then great. But we know at least one of them will be, and we want to keep the one that is in the interval. But if something is outside the interval, that's not going to be valid. So the only one that's going to stay inside the interval is this one here. Mean value theorem is virtually the same steps. Find endpoints, find average rate of change, find the derivative, set them equal to each other, and solve for x. It's just that Rolle's theorem is more restrictive. It has to be an average rate of change of 0. But mean value theorem can be average rate of change of 0. It can be other slopes. It doesn't have to be 0, but Rolle's theorem has to be an average rate of change of 0. Okay, I want us to do one more graphing before class ends. So can we go to page 10 and try the last problem there? Yep, number 7. So the order pairs, that's easy, right? You can just plot all those points. The second and third and fourth statement, they all refer to f prime. Let's see if we can put that onto our f prime sign line to get a visual idea before we start putting those, before we put all this onto our graph. So let's read the second statement here. F prime of x is less than 0 for x is less than -1 and x is greater than 2. What does f prime less than 0 mean?
This concat can't be.
Not
Slope's negative.
slope is negative. So where's slope negative? Another way to say less than is to the left. Okay, so it's to the left of -1 and then to the right of 2. So you know these are critical points, right? Because these are boundaries that are helping us. Are you guys able to create this picture from the statement, right? So that's, make sure we can do that.
We got here what is in between, right?
Yeah, hopefully that will show up later. F prime -1 is equal to 0. F prime of 2 is equal to 0. What is that telling us about these critical points?
There's. Absolutely.
Slope 0, yeah. So you know it's a smooth curve. We don't know if it's a relative max, relative min, but we know it's not a sharp turn, it's not a vertical asymptote, it's not a hole. It's going to be a slope 0. Okay, smooth curve all the way through, at least around those endpoints, those critical points. Okay, next statement. F prime of x is greater than 0, or -1 is less than x is less than 2. Positive slope,
In between.
-1 and 2, yeah. Okay, second derivative sign line. We have the last two statements providing information about it. F double prime of x is less than 0, for x is less than -4 and x is greater than 0. How would you say this a different way? Negative, right? Less than 0 is negative. Negative, second derivative is concave down. Good. So concave down where?
Left of -4 for credits.
Okay. Last statement. F double prime of x is greater than 0, or -4 is less than x is less than 0.
Oh, it's weird. The concavity's up. Okay,
Concave up. Good.
to the right of 4 and 2.
Yeah, between -4 and 0. Good. Now, sometimes it's hard to try to do both of these at the same time. So what you want to do is you want to put the emphasis on the f prime. This is going to help sketch out the path of your graph. And then you can go up and clean up that path a little bit. But we don't want to do this first. If we do this first, we're going to get thrown off by curvature that is not part of our graph. So we want to let this be our guide. Okay, this is going to be our draft. Our draft is going to be coming from this f prime. So you know that your graph is going to behave this way in terms of slope. It's going to fall until we hit a relative min at -1. It's going to rise until it max at 2, and it's going to fall again. So our graph is going to basically look like this. The curvature may not be right, but it's going to follow this path. It's going to be falling, rising, falling. So now we can go back and retrace the graph with more information. How do we want the graph to look up until -4? Concave, but it's got to maintain this decreasing, right? So it's got to be decreasing the whole way through because we've established what our slope is going to be. But then from here, we're going to change over to what? So concave up to 0. So we can kind of, we're basically following the path, but we're just matching the curvature that we want. And then to the right of 0.
Concave and use numbers.
Concave what?
Concave down.
Concave down again. Okay, notice we're still following the path. We're just giving it more curvature. Now, let me ask you this. Why can I not do a full concave down and do it this way? Because that feels more correct, right? Because that full concave down there. Why can I not do this part?
No.
We do have enough information. What do you know about the slope to the left of -1?
Oh, we can continue on.
It needs to be what? Decreasing, right? So if I do a full concave down, then this is showing me what slope. That's not right, correct? So make sure that you don't veer too far off from your path. You have your slope path. Right, help session this afternoon and tomorrow morning. Come get your phones.
Okay. But if you get the drawing part wrong, if you get everything else right, what balance?
Yeah, I'll still
Yeah, I'll still give you, partial credit, yeah.
Okay.
But the more information you show me, the more I can give you partial credit, right? So show me the sign lines and I can.
Are you doing anything new to add on to this test before?
Yeah, we have, 3 more sections to learn before the test, yeah.
It was add on to this.
Add rate, right?
It's a very good one, I'm not sure.
That was good. Concave down, concave up, concave down, yeah.
Okay, I wasn't sure about this part.
Okay.
Yeah, the arrows at both ends.
Arrows at both ends, that's right.